Traveling at over 300 kilometers an hour, the TGV is the pride of France's high-speed railway. Now, to create the next generation of trains, engineers are planning a daring experiment. They want to build the fastest train in the world. A bullet on wheels that will travel at over 500 kilometers an hour. When it comes to big speeds, nothing on rails will come close. The TGV owes its success to 4 key inventions, found in a series of landmark trains. Each one carries a major technical innovation that allowed engineers to push the speed limit further and further. One by one, traveling up the scale, we'll reveal the incredible stories behind these machines and the inventions that allowed them to go ever faster. 4 ingenious leaps forward, from the first intercity railway to the fastest train on the planet. In France, nothing beats the TGV. For most journeys, the train à grande vitesse is the quickest way to travel. For engineer and train enthusiast Jem Stansfield, this machine is nothing less than revolutionary.
I've got to say I'm a fan of the TGV. I like the look of them. I like the kind of classic streamlining along them. You can't help but be gobsmacked by the power of them. When you realise that through those overhead wires, they're sucking the power of maybe a small town. And you look here at all the people just sat in comfort, chatting, yet travelling at 300 kilometres an hour. No one bats an eyelid.
At the TGV control centre in northern France, operators guide nearly 500 high-speed trains across the network. France has almost 2,000 kilometers of high-speed track, the biggest network in Europe. But now the French are going to make it even bigger. An ambitious expansion project will triple the size of their network and extend it even further into 7 European countries. They'll build new tracks, drill tunnels through mountains, and to slash journey times, they'll introduce a new, faster model of the TGV called the AGV. The AGV will use 30% less energy, but will carry more passengers at a greater speed. And to test this new technology, French engineers are building a unique experimental train that will push their new components to the limit. In 3 days' time, this supercharged version of a TGV will attempt to break the world speed record for trains of 515 kilometers an hour. To understand how the TGV can travel at such speed, we need to go back in time. In early 19th century Britain, a group of businessmen want to build the world's first intercity railway. But they haven't quite worked out how to power it. In the 1820s, northwest England is booming. The mills of Manchester are working flat out to supply textiles and other goods to the world. But transporting them from the factories to the port of Liverpool is a painfully slow business. By canal, the 50-kilometre trip can take up to a month. To speed things up, the businessmen of Manchester and Liverpool take a gamble on a new technology. They plan to build a railway and power it with steam. Their first idea is to attach a rope to a train of wagons and hook it up to a steam engine sitting beside the track. This will pull the train along the rails like a cable car. There has to be one engine almost every kilometre, or the cable in between becomes too heavy to pull. To get from Liverpool to Manchester, they'll need 54 engines. And if just one of them breaks down, the whole railway grinds to a halt. The railway's chief engineer, George Stephenson, believes a better place for the engine is right at the front of the train, in a locomotive. Railway historian Anthony Cools explains.
He was itching to be given the chance to show that steam locomotives could pull trains long distances with a large amount behind them.
To prove that locomotives are the way forward, Stephenson and his son Robert plan to build their own, called the Rocket. To do this, they must overcome a major challenge. Early steam engines don't produce enough power to pull a train laden with heavy goods at any decent speed. To solve this problem, Stephenson needs to get more steam out of the boiler. To show how he does it, Jem Stansfield has gone back to the workshop.
Obviously, to produce steam, you need to heat water. But what's the most efficient way of getting the heat from your fire to the water in your boiler? Well, here, I've got two almost identical pans. Except in this one, I've welded 14 tubes into the base of it. Now, I'm going to put half a pint of water in each. Turn the gas on full for each one. And when they boil, the steam's going to come up through these holes and turn these turbines. So whichever turbine we see go first is the pan that's been heated most efficiently. Now already, the top of this one is misting up quicker than the top of that one, which makes me think the water in here is heating up more quickly. There's steam coming up through here now. There's absolutely no steam here at all. It's actually safe to the touch. How very satisfying. This little steam engine's up and running nicely, whereas that one hasn't got off the starting line yet. And the reason for this difference is the efficiency of the heat transfer from the fire to the water inside the boiler.
By running pipes through the pan, Jem has increased the amount of hot metal touching the water, so it boils faster and produces more steam.
So the water's being heated around the pipes as well as round the edges. And as you can see, it's a pretty nifty way of doing it.
Stephenson uses this idea on the Rocket's boiler. Instead of a single pipe, this boiler has 25 pipes carrying the hot gases from the furnace. These vastly increase the contact area with the water. Now the same fire generates much more steam to power the pistons and the wheels. To get even more power out of his engine, Stephenson recycles the steam. Instead of releasing it from the pistons into the air, he feeds it through a pipe back into the rocket. As the steam blasts up the chimney, it sucks more air into the fire. This makes it burn hotter and generate even more steam. With its blast pipe and multi-tubular boiler, the Rocket is a turbocharged powerhouse. In October 1829, at Rain Hill near Liverpool, Rocket goes head-to-head with 4 other engines in a bid to prove that locomotives are better than stationary steam engines. The Rain Hill trials draw thousands of spectators from all over England.
There was a high sense of anticipation and excitement. It was almost like race day. People put bets on which locomotives would be the best ones, and the form of the runners was studied keenly. There were 2 main runners, really. There was one called Novelty, built by Braithwaite and Ericsson of London. It was the crowd's favourite. They referred to it as the London engine. It was light, it was fast, but it didn't really have the guts to pull the skin off a rice pudding.
When Novelty retires with a boiler leak, it leaves only one contender for the £500 prize.
George Stephenson and Robert came on with Rocket, absolutely tore the field apart. It dashed along, running at nearly 30 miles an hour.
Rocket reaches an astonishing 46 kilometres an hour. The fastest machine on the planet. And it can pull 3 times its own weight with ease.
This is a kettle on steroids. The combination of the multi-tubular boiler, the blast pipe which you can hear chopping away, those were enough to make the locomotive the absolute winner and claim that bounty prize for George and Robert Stephenson.
Rocket's victory is the starting gun for a new age of speed. When the railway opens, Rocket carries goods between Manchester and Liverpool 10 times faster than a canal barge. And a few months later, it powers the first scheduled passenger railway in the world.
Every steam locomotive built in the last 180 years throughout the world owes its origins to the combination of the multi-tubular boiler and the blast pipe. Really, that lays the foundation for the steam locomotive as we know it.
The genius of the Stephensons starts a transport revolution, powered by steam. Like Stephenson's rocket, the experimental TGV in France is in a race to become the fastest train on the planet. To beat the world record, it will have to travel at over 515 kilometers an hour. As on Rocket, the engines hold the key to success. The experimental TGV is the most powerful train ever built. At the front of it sits a souped-up TGV locomotive. Behind it, 3 double-decker carriages, each fitted with advanced motors from the next generation train, the AGV, to give extra speed. A second TGV locomotive is hooked up to the rear. All in all, this train has more engine power than all the cars in a Formula One Grand Prix put together. Feeding electricity to these engines is a real challenge. Engineers rely on a metal contact extending up from the trains called a pantograph. It's the unsung hero on the TGV, as Jem Stansfield discovers at the TGV Service Centre in Paris.
These are the bows of the pantograph. Now, they have the absolutely pivotal role of taking the electricity from the overhead catenary line down to the motors that drive the train. They have an extremely difficult job to do because they have to cope with both the frictional rubbing of the wire on the top of them, but also the vast amounts of current it's transferring mean that there's electrical arcing and wearing through that. For that reason, graphite is the optimal material to use. It's both low friction with regard to rubbing and is very good at transmitting electricity.
Graphite is an excellent conductor, but it is also quite soft, which creates a problem with the power lines. A straight power line would wear a groove into the soft graphite strip. So on the TGV, the line crosses from one side to the other to wear down the strip evenly. But if the graphite gets damaged, the wire can snag on the pantograph and rip it to shreds. To stop this from happening, the pantograph on the TGV is pushed up to the wire with compressed air. If any part of the pantograph is damaged, the air escapes, and the contact drops down before the wire can snag. The pantograph on the experimental train has to draw twice as much power as a traditional TGV through a contact the size of a fingernail. It will race along the overhead wires at over 500 kilometers an hour, which creates another problem.
Now you can see as that train went through, it's wobbled the overhead catenary power lines, and that's because that's where it picks up the electricity. The pantograph runs along it and disturbs it. Those hanging weights there perform the vital task of tensioning the overhead power lines. Without them, those lines would sag too deeply for the pantograph on the top of the train to accommodate the difference in height.
On a regular line, the weights stretch the overhead wire to a tension of 2.5 tons.
Now they perform a vital day-to-day function here, but for a world record-breaking run, you're going to need more tension than that. You need to keep the wire very taut indeed to prevent wobble. 4 tons of tension is what they would require.
The experimental TGV is finally ready. In 2 days' time, it will attempt to break the world speed record. Back in 1829, Rocket proves that steam locomotives are the future of railways. But as trains get ever faster, they face an invisible obstacle: the air. To help trains outwit this enemy, engineers must reinvent their shape. At the start of the 20th century, there's nearly 1 million kilometers of railways around the world. But in the 1930s, rail travel faces serious competition. Motor cars become more affordable and draw customers away from the train. In Britain, the London and North Eastern Railway decides to fight back. They want to build a new, faster train that can whisk passengers from London to Edinburgh in less than 8 hours, 2 hours faster than a car. They hand the job to their top engineer, Nigel Gresley.
Nigel Gresley was a real character. He was a big bear of a man. He's well over 6 foot. He was really called the Gentle Giant. He was a very much hands-on type of person. He'd started from the very bottom. He worked his way up through the engine workshops, so he knew the trade inside out.
To make his trains faster, Gresley could simply use more powerful engines. But bigger engines burn more coal, which puts up the price of tickets. Gresley has to find a better way to speed up a train. He realizes that wind is the key.
What they found was that the wind was hitting the front of the train basically and being pushed down the side of the train, and this was restricting the speed of the locomotive and also the train. We couldn't go very fast, probably about 50-60 miles an hour was the top speed for these.
To beat the wind, Gresley steals an idea from the competition.
He went to see his friend Ettore Bugatti. He was a racing car designer who was an expert at streamlining.
Bugatti designs cars with wedge-shaped noses that make them slip through the air and go faster. Inspired by Bugatti's ideas, Gresley draws up plans for a sleek new train, the A4 Pacific. It's a steam train with totally new clothes on. To slip through the air hitting the front of the train, Gresley gives his loco a wedge-shaped nose, just like Bugatti's cars. To prevent the wheels from stirring up the airflow, he covers their top edges with elegantly streamlined panels. And to stop turbulence forming in the gaps between the carriages, he covers them up with sheets of rubber. Now Gresley has a train that's not just powerful, but also aerodynamic. The streamlined A4 Pacific looks unlike any train that's gone before.
This is part of Gresley's great idea for streamlining. It was a wedge-shaped front end, as you see, where it deflects the wind over the top of the engine and away from the side of the carriages. Also, you've got this beautiful curvature here, which again takes the wind away.
Gresley builds 35 A4 Pacifics and rolls them out between London and Edinburgh. They reach speeds of 145 kilometres an hour. Much faster than the cars of the day. In July 1938, an A4 Pacific called Mallard steams out of Grantham in an attempt to break the world speed record.
It would have been extremely hot, very, very noisy, it's hard to hear yourself speak. You're going at extreme speed, over 100 miles an hour. Gradually it crept up from 103, 109, 113. It was going faster and faster. And it was finally shut down because it was becoming too dangerous. 125 miles an hour. When they checked the figures afterwards, it was actually 126.1 miles an hour.
Thanks to its streamlining, the Mallard reaches 202 kilometres an hour and beats the world record. For steam trains, it's a record it holds to this day. In France, the experimental TGV attempting the world record is thoroughly streamlined. The windscreen is completely flush with the sloping nose. A spoiler diverts air around the wheels. And just like on the A4 Pacific, rubber seals cover the gaps between the carriages.
It needs to be so slick for a high-speed attempt because air doesn't seem very heavy, but it actually weighs over 1 kilo per cubic metre. And if you look at the size of this train and the speed it's going, it has to shift getting on for a couple of tons of air every single second of its journey.
The air in front of high-speed trains creates an unusual challenge for the engineers expanding the French network. To reach countries like Spain, they have to build tunnels through the mountains. But tunnels create problems for high-speed trains. On a well-designed train, most of the air rushes over the top and the sides. but in a tight tunnel, the air can't escape and gets squashed. It turns into a shockwave that shoots ahead of the train at the speed of sound. Like a bullet from a barrel, it exits the tunnel with a sonic boom that rattles the neighborhood. This is a rare recording of tunnel boom. It takes over a minute before the train itself emerges from the tunnel. To deaden the boom, engineers install a canopy over the tunnel entrance that has slots cut into its roof. The holes disperse the energy of the blast, so it leaves the tunnel with a whimper. Here in the Pyrenees, engineers have already installed the slotted canopies. Soon the AGV trains will whiz through them at up to 350 kilometers an hour and emerge without a boom. To break the world record, the experimental TGV will have to run much faster than this. Engineers aren't taking any chances. When the TGV makes its attempt on the world record tomorrow, there won't be a tunnel in sight. Back in the 1930s, the Mallard streamlined shape nudges train speeds past 200 kilometers an hour. But when Japanese engineers try to push trains even faster, they face a fundamental problem. At high speeds, train wheels behave erratically, and the Japanese have to get them back on track. In the 1950s, jet planes revolutionized long-distance travel. In Japan, they whisked travelers 400 kilometers from Osaka to Tokyo in less than 2 hours. To compete with the jets, Japanese railway engineers designed the Shinkansen, also known as the bullet train. But their prototypes have a serious problem. At certain speeds, the carriages start moving from side to side, inducing a snake-like motion. This vibration can become so violent, it derails the train. This phenomenon is called hunting, and the Japanese have to solve it. They give the job to Tadashi Matsudaira, an engineer who solved similar vibration problems in fighter planes. Matsudaira has a hunch that the shape of the train wheels is to blame for the hunting.
Now, it's all right building yourself a railway, but unless you're confident that the trains are going to stay on the tracks, it's not much use. And railway wheel design is a bit more cunning than you might think. If you imagine if you were to use just car-type wheels, flat, ready to go, put them on the track, and they do just what you'd expect. They stay on there for a little bit, but then they come off. So what about making wheels with a bit of a cone on them? Rubbish. But if you turn the cones round and have them sat like this, it's spookily good. Have a look at this. It looks almost magic. Obviously it's not magic, it just kind of looks like it.
The subtle conical shape of the wheels is the key to keeping a train on its track. But on scale model tests, Japanese engineers find that at high speeds, these wheels start swinging from side to side and slide off the rails. Matsudaira realizes that the key to the problem lies in the train's suspension. With nothing to absorb the sideways motion of the wheels, the problem just gets worse. Matsudaira's plan is to attach finely tuned steel springs to the axles. This should keep the train on track, in theory. In March 1963, Matsudaira puts his springs to the test in a high-speed run with a real Shinkansen. An army of technicians keep watch as the train heads out onto the track. As the train accelerates, the instruments pick up vibration building up in the wheels. Matsudaira himself has his hand on the emergency stop button, but decides to keep going. And sure enough, the train settles down and delivers a flawless run, reaching a record speed of 256 kilometers an hour. The new suspension is an outstanding success and keeps the Shinkansen firmly on the track. Over the next decades, Japan Railways rolls out the high-speed service across the country. Fast, safe, and nearly always spot on time, the trains between Tokyo and Osaka carry 80,000 passengers a day. 4 times more than the planes. The legacy of the Shinkansen is still visible on the TGV today. At the technical center on the outskirts of Paris, a TGV is about to have its wheels replaced. The French have built a jacking system that can lift the whole train up at the touch of a button. It takes just 10 minutes to raise the train's 2 engines and 8 carriages 2 meters into the air. Now the mechanics can get at the 4-wheeled trolleys that support the carriages, called bogies. Their springs still use Matsudaira's design. But there's one big difference in the way the bogies are arranged under the train.
Conventionally, you'd have a bogie at the front and back of each carriage and they'd get linked together to form a train. But here, each bogie has 2 carriages on it. The bogie is shared by the front and back of adjacent carriages, and they're linked together.
Traditional trains have 1 bogie at the end of each carriage. This is a disadvantage in a crash. The carriages can jackknife against each other and derail the train. But on the TGV, the bogies sit between the carriages, which makes for a stronger connection. The train is more rigid, so in a crash, it's more likely to stay straight and on the tracks, keeping the passengers safe inside. The bogies on the experimental TGV also sit between the carriages. But as well as holding the carriages together, the 2 main bogies are fitted with a secret weapon. 4 1,300 horsepower motors from the next generation train, the AGV. The engineers hope that these will give this TGV the extra power it needs to break the world speed record. Back in 1963, the Shinkansen proves that trains can be super fast and stable. But as French engineers expand their network to run faster trains, they face a new problem. They must design a foolproof signaling system to make sure their trains don't crash. On a foggy day in December 1933, France suffers the worst train disaster in its history. An express train plows into the back of a train stopped near the village of Lagny. 200 passengers lose their lives. An investigation reveals that the signaling system is to blame for the disaster.
The French used a simple electrical system when they wanted to alert the driver of a train. When the signal was down and they needed to attract the driver's attention, a metal strip down the centre of a section of track was electrified. And on the underside of the train would be a metal brush like this.
When the brush makes contact with the strip, it triggers an alarm in the driver's cab.
Let's see how this one goes. So there's the train off round the track. It's got its pickup underneath, waiting to collect its pulse of electricity. Well, certainly if I was driving the train, there's no way I'd have missed that kind of signal.
But as the investigation into the Lagny crash reveals, the system has a simple flaw. It's not weatherproof. As the express steams towards Lagny, central control activates a stop signal, but thick fog hangs over the tracks so the driver can't see the signal. He now relies entirely on the safety switch. But moisture in the air has frozen over it in a thick layer of ice. As the train passes, the brush can't make contact with the metal and pick up the warning signal. The steam whistle inside the cab stays silent. The last thing the driver sees is the back of the other train. The next generation of TGV trains will travel 3 times faster than those that crashed at Lagny. Stopping them is a phenomenal challenge.
If you want to stop a train like the TGV, you need enormous brakes and lots of them, which is where these huge brake discs come into play. There are 8 of them per bogie, and they turn with the wheels. And when you want to stop the train, you have to clamp onto them these brake pads. Then the whole energy of the train has to be absorbed as frictional heat on these discs. Now that is an awful lot of heat, and these get extremely hot.
But even with all these brakes, it takes 3 kilometers to bring a TGV to a halt. This puts an enormous amount of pressure on the driver. At this TGV training school in northern France, drivers are learning how to handle the new, faster AGV trains. In the simulator, they'll find out that the speed of this train is simply too much for the human eye.
We're heading downhill at the moment, and it feels exactly like a real train. We're approaching 300 kilometers an hour, and his target speed is 320. Now at that speed, we're going at nearly 100 meters a second, which means that you just don't have time to see trackside signals.
With over 800 passengers on board a new AGV train, the signaling has to be 100% reliable, even in extreme weather. Engineers of the French high-speed expansion project are rolling out the latest in signaling technology. It works without any physical contact. They install transmitters at regular intervals along the track. These send electrical signals through the rails, which creates a magnetic field around them. As the train passes, an onboard sensor picks up this magnetic field and relays the information to the driver in the cab. And if this signal ever disappears, the onboard computer automatically slams on the brakes. The drivers at the training school must learn to completely trust the onboard signaling system.
If something happened 200 meters up ahead, you have literally about 2 seconds to register it and do something about it. That's simply not enough time, which is why Christophe here is driving this train almost just completely from these control panels. He could shut a blind on that window and he would still be as good a driver because there's very little he can do. You see that corner up ahead? You're there before you can do anything about it.
As the experimental TGV waits on the starting line, closing the blinds is the last thing on driver Eric Piéjac's mind.
On départ dans 1 minute.
To break the world speed record, he needs to power his train to over 515 kilometers an hour.
On n'a absolument pas le droit à l'erreur, il faut absolument qu'on réussisse parce que tout le monde va nous filmer et tout le monde va être là.
As Eric cranks up the speed, engineers on board monitor 350 sensors distributed throughout the train.
On a fait passe à 360. 360. Correct.
Traveling at airline speed just inches from the ground, the engineers are putting their lives in the hands of the components they have designed.
480 plus 5. 4, 8, 5.
Donc c'est au cours de la marche qu'on a senti que c'était de mieux en mieux et ça va relativement vite, ça va très vite dans le temps. Et c'est là qu'on se dit, on a gagné, on va réussir et on va le faire.
Plus à 500, 515. 5, 5.
As the train hits 515 kilometers an hour, it shatters the old record and keeps going.
Allez, pas plus, on y va. Allez, bien. 150. 570, c'est dans ma boîte.
Finally, Eric eases off the power.
L'attention de tous, après contrôle et validation, la valeur officielle de la vitesse atteinte dans notre marche est de 574,8 km/h. Je répète, 574,8 km/h.
It's a staggering new world record and a triumph for the team. The spectacular test has shown that the new AGV train will keep French railway engineers ahead of the curve. Today, the TGV is already faster and safer than the aeroplane on most journeys. As high-speed networks expand across Europe, even more people will put their lives in the hands of these amazing machines. Since the day of Stephenson's rocket, trains have gone from fast to faster to now the world's fastest. When it comes to big speeds, nothing on rails beats the train à grande vitesse until someone builds an even faster one.